Sorry.
Here's the like finding X. It's like, how do you like, because mine is like, there's this count. It's like, you get a count of everything. You only have one thing that such as average.
Can I see that from the back? You like calculate it all.
Just after I got that, that's that.
Got one more done this morning. I think I insert that. So, just one test. Yeah, I'm still, I gotta get kind of, I'm still not comfortable with some of the stuff. Like, because you can see just from the layers, when it has the super,
Yeah.
and I'm not understanding exactly.
Yeah, we have to fix this. Yeah, there's actually a bug. Doesn't show this. So this is what I did. So if I can do like that string, you just have an iterator that's full. You haven't computed it yet. You can just go through the whole table.
What is this aggregator? What's the
So this aggregator is just to find out if it's your strings that we're doing. And it's the one that's like, okay, I'm going to merge the tuple into the group.
okay?
Right? And so then what happens is like when you're doing like a sum, right? You need to take your previous like sum of values and add to it, right? And so this just goes through each tile and just adds them up. And then when you get done, after you go through the table, create an iterator out of that and start it up, and then you can return the next. And the next time it comes up and says, hey, the next, this is the null. So we'll redo all that stuff, and it will just go and get the next. But I found a bug that I gotta fix. It doesn't, it passed all the tests, but he has these like set children and get children. Well, if he changes the child, right, and we've already viewed it, so I gotta fix that. Set it to null again. It's an easy fix.
Alright, let's get started. Last time we finished a bunch of join operators, like some basic ones like nested loop, index nested loop, block, page-oriented nested loop, block nested loop, and so on. So we didn't finish the sort merge join and hash join in last lecture, so we will reiterate everything here again. So the sort merge join is based on like sorting two relations to be joined based on their join predicate. Then if both relations are sorted on the join predicate, you can basically use the merge method we mentioned in like external sorting. It's basically the same thing except that you do not check for the condition to put the next tuple into your sorted run. Instead, you basically check the join attribute on the join conditions. Okay? So basically, this can only be applied to equijoin and range joins. Okay? So the general scheme is basically looks like this. So basically, if you have two sorted runs like this, R and S, then you have two pointers initially at the beginning. Then the relation on the left is called the outer relation. It's the same analogy to the outer relation in nested loop. Okay, So that's the relation you use to prove the other relation. So how do you determine what's the range in the other relation? Basically, you look at the current pointer and start moving that pointer downward. Okay, and you basically emit all the tuples with a matching key here, right? So basically, for the first one here, you are looking at basically. Let's see if this works better. Yeah, basically for this one here, you basically look at another color. You look at this one, the first one here. Can you see the pointer actually? Okay, let's do this. So basically, you look at the first one here, okay, and it has a matching key, so that's a join result. Then you move the pointer downward to here. Then it's still matching key, so that's okay. Then you move it down, okay. Then once you do that, since currently the key on the right is greater than the key on the left, so you start moving the pointer on the left. So whenever you find the two keys doesn't match, you move the pointer that has a smaller key, okay, downward. So basically, you move the pointer here downward to here, to the next one, right? So it's going to be this one, right? So now instead of that, your pointer is pointing to here, okay? So since this key is the same as the previous one, you have to rewind your current pointer on the right back to the first one here, okay? So basically for each range, if you have match, you kind of have to remember where the first key is, so that in case you have some duplicate keys on the left, you need to rewind the other one back to them. Rewind the pointer on the right back to the first key in that range, okay? So then you repeat the process, so basically you produce this tuple and this tuple, okay? These two tuples. Then the next thing, then next thing that happens is that your pointer is now pointing to here. And for the left, you've already, since you finish everything on the left, so now you compare 1 and 4, it's still 1 is smaller than 4, right? Then you move the pointer that points to 1 downward to 2, okay? And 2 is still smaller than 4, so you move it further downward, here, and here, until you reach here, right? Reach 5. Then you find that 5 is actually larger than 4. So instead of moving the pointer on the left, you start moving the pointer on the right, okay? In each step, you always, if the Q2 keys doesn't match, you always move the pointer that has a smaller key, okay? So then you have a joining record, okay? You have a joint result. So that's basically the process. Basically, so for sort merge join, as we see here, it's possible that you get a full Cartesian product, which is the property of your join itself. Like if your join happens to be your join result happens to be the full Cartesian product, then you have to rewind the pointer on the right again and again and again, right? But in a better case, like if you are joining two keys, like a primary key and a foreign key, then you know for each of the record on the left, you only have 1 on the right that matches it, right? So then in that case, basically you just linearly scan the two arrays or two files, right? So then you just have a linear path, okay? So that actually really depends your join cardinality, how large your join size is, right? Okay, so let's see a concrete example here. I've copied the schema of reserves and sailors here so that if you do need to look at the numbers, it's here, okay? So I'll start explaining why this is the case. So suppose you have these two tables. The table on the left is the sailors table, and the table on the right is the greetings table, okay? And you are trying to join the two tables based on their the foreign key and primary key in these two tables, basically the SID. Then what is the cost of this sort merge join? Okay, Yeah, just some heads up. So basically, I've been updating these slides constantly, especially this one and the next one, because there are so many formulas which can have like slight inaccuracy. So I would suggest if you want to have like if you want to make sure your slide doesn't have any mistakes or errors, you might want to just maybe print or save it after these couple lectures, okay? Because I'm constantly making changes. Like I just updated this morning. Okay. So yeah. So for here, the first part would be sorting the two relations because originally the two relations are in key files which are unordered. Then you have to sort them based on the SID. So that involves external sorting, right? So basically, the cost of sorting the first table would be this one. Okay, here it's gonna be the first one here. So basically, you compute how many passes you have to like fully sort this relation. So here we are assuming you are using tournament sort, and actually there's a 2n divided by b, 2 times n over b minus 2, right? But you can basically ignore that small difference. That doesn't matter a lot, okay? So basically here you can just compute that as this. So in the first pass, you're assuming, so you're using a tournament sort, and on average, you have a run size of 2m over b, okay? Then this is the size of, the number of runs after the first pass on average. Then you take a log factor where your number here is m over b minus 1, right? Then that's the number of passes after pass 0. So you add 1 to that. That's the total number of passes you need in the external sorting of the savers table. Then you times that by the size of savers table. You get the cost to sort this particular table. Okay, so it's 2 times n1 over b times the number of passes. And the same goes on, the same thing happens to the reserves table. Basically, you use the same external sorting algorithm to sort it. So the cost looks like this. So what is the last term here? N1 over b plus N2 over b. Okay. That's basically the cost to scan the two tables. Okay. So why is that? Because here, for the second table, basically each record is only going to have one matching record on the left because the SID is a foreign key. The reference is the other table, right? So you only have one-to-one matching. So that means you never have rewind during your merge process. So that means basically the two sorted files are only scanned once. So so the cost would be just you scan the first file once and you sort the second file once. The only thing that's different is that except that you basically scan the two files concurrently. Okay, you scan them at the same time. You could be fetch one page here, one page there, right? Just like interleaving the IOs. But still, the total cost will be n1 over b plus n2. So yeah, and here's a side note, like the cost of scanning could be up to n1 over b times n2 over b if you are so unfortunate to have a full Cartesian product, right? It's up to, but it's highly unlikely, right? In reality. And if you plug in some numbers like the 1,000 pages, that's n2 over b. 1,000 is n2 over b, and 500 is n1 over b. Okay, so basically we have n1 over b equal to 500, and n2 over b equal to 1,000, right? Right. Then with either 35, 100, or 300 buffer pages in your buffer pool, you basically still need 2 passes for both tables. Okay, so then that means the number of passes is going to be 2, and if you plug in all the numbers, you end up with a join cost of 7,500 IOs. Okay, and that's to be compared with block nested loop. Okay, so depending on your number of buffer pages, you could end up with 2,500 IOs or 50,000 IOs. Okay, that differs with the number of buffer pages you have in your buffer pool. Okay. Of course, it's definitely better than page-oriented nesting loop or the simple nesting. Okay, we can try to optimize the whole process a little bit. Like noticing that in your external sorting, you still have a merge process in the last phase. Okay, in the last phase, you basically merge a bunch of rounds into one single round. That's your sorted file, right? So during this process, you are actually producing the tuples on the fly. Okay, so instead of writing them to the external file and then read them back to do the merge of sort merge join again, you could like combine these two processes, right? It's something like this. So basically, suppose in your last pass, before your last pass for the relation R, you have a bunch of sorted rungs. Okay, so basically you have a bunch of sorted rungs like this. And for S, you also have a bunch of sorted rungs like this. That's the last pass of your external sorting. Okay, and once you do that, in your buffer pool, you split your entire buffer pool into two parts. Okay, one part is for the rungs of R, and the other part is for rungs of S. Then for each of the rung, you create a buffer page for input. Okay, so basically, suppose this is for R, this is for S, right? And then you have a bunch of this. Then you basically, each time you get one page out of each rung into the buffer pool, okay? Something like this, right? You have one page of each rung put into the buffer pool, and you start the merging, like you like using a min heap or something else, right? Like you just try to find the smallest element you're currently pointing to, right? Then basically you are producing those tuples on the fly. So at any time, you have one next tuple in for R and one next tuple for S, right? And what are those? Those are basically the pointers. Sorry, the tuples you are pointing to during the merge of your sort merge, right? If you think of that, it's actually so. If you think about the whole process, when you do the merge of sort merge on, you have 2 pointers. They can be basically, so if you think of the next tuple as the tuple that your pointer is pointing to, okay, then basically you can just compare these 2 current tuples, right, and about the keys. So suppose I know, suppose I have suppose the current tuple for R has a key of 4, and the current tuple of S has a key of 5. Okay, then you know you need to increment the pointer in R, right? So what you do is that instead of like incrementing anything in S, you do not modify any state in the S part. You basically just try to get the merge phase of your the merge phase of your external sorting in the last pass of R to get the next tuple. Okay. So what happens is that you try to find the smallest key among these rungs in R, and then you produce the next tuple, and that becomes the current tuple your pointer pointing to in the merge phase of sort merge. All right. So that's basically something like this. So suppose you produce 5 here. Okay, then that 4 is basically discarded, Then you have a current tuple with 5. And then basically you just incremented the pointer in R. Then you have two tuples with matching key. And then that's the join result you want to out. Okay. After that, so if you have matching keys, then you need to increment the key in S. Okay. So you basically discard the tuple 5 here. You try to find the smallest key among the rounds in S. Then you extract the key out of the next tuple. Suppose you get a 6, right? Then your pointer just moved to a new tuple of 6 in S. Right? That's the refinement. So basically you combine the merge phase of external sorting. Sorry, the last pass of external sorting and the merge phase of sort merge join into one loop. Okay, it's a little bit complicated, but it might take a while to think about it. Right, and one thing to note here, remember in the merge phase of sort merge join, sometimes we might need to rewind back to the very first tuple we had, right? So that actually causes a little bit of problem here because in the last pass of external sorting, you cannot go back in your stream, right? So once you produce the next tuple, the previous tuples are discarded, right? You might not have a chance to go back because the corresponding tuple could be on a page that you have just discarded, right? So that means if you do have a matching key for the first time, you probably need to start recording the tuples in S somewhere, maybe in the external memory or in memory somewhere, right? That's the caveat of this. But suppose you just ignore that part, let's just simplify the problem a little bit. Let's just ignore the need for a rewind. Okay? Suppose you are just joining primary keys, then you don't have that problem. Then basically you just iterate through the two streams once, okay, the two sorted files once. Then the requirement for if you want to do the whole process purely in memory, the requirement would be, so suppose m over b is greater than square root of L, where the L is the size of the larger relation, RNS, right? The larger one of RNS. In this case, it would be results, because results has a 1,000 pages, right? So suppose m over b is greater than square root of L, then using the tournament sort, where you to produce rounds of length on average 2m over b in pass 0, then you can easily calculate the number of rounds of each relation is smaller than m over 2b. Okay. So what that means? That means basically, so if your m over b is greater than square root of L, then L divided by 2m over b is going to be smaller than m over 2b. Okay, that's just you just substitute the numbers into the equation. Inequality, then you get the result. Then that's basically the requirement for if you want to do the whole process in 2 passes. Okay, if you want to do the whole process in 2 passes, that's a requirement. Okay, but anyway, you could also like do that in multiple passes, then it could be larger. Right? If the relation is actually larger, then it's multiple passes. So for the example here, so you can convince yourself. Actually, it does satisfy this condition. Okay, m over b is greater than square root of L, because square root of 1,000 is going to be roughly 30-ish, 30 to 40 pages, right? It should be less than 35. Okay, so basically this is smaller than 35. Then, as we said, if you use a buffer pool with 35 or 100 or 300 buffer pages, then this condition holds. Okay, m over b greater than square root of L holds, right? Then what happens is that you can still finish the sort merge join in 2 passes, and even with the refined one, because the refined one actually you can only have fewer runs per pass. Okay. Then basically you can apply this optimization in the second pass. As a result, the cost goes down from 7,500 IOs down to 4,500 IOs. Okay, why is that? That is because, so remember here, you only do pass 1 for the first 2 terms. Okay, so that's going to be 1 less than 1 plus log something, right? So that's basically your cost is going to be 2n1 over b times 1. Okay, 1 is 1 fewer pass. Okay, and plus 2n2 over b times 1. Okay, and the last pass is basically combined with the merge process. So as a result, you basically read everything once, and that's it. You basically just read everything once. Okay, so then you basically add just n1 plus n2 over b. Okay. If you plug in the numbers, n1 over b is 1,000, n2 over b is 500. So this comes to, the whole thing comes to 3 times n1 over b plus n2 over b. Okay, so that's 3 times 1,500. That gives you 4,500. Okay, so if you apply this refinement here, then your cost of solver drawing goes from 7,500 IOs down to 4,500 IOs. So, and also notice that, so in practice, the cost of solver drawing is really linear. Okay, in a benign case like this, like if you are joining two relations that basically have constant degree. Here, degree means the number of tuples in the other table that joins 1 tuple on the left. Okay, so basically, how many tuples you have in the second table that join every tuple on the left. So if this degree is kind of constant, and your table is moderately large, which is always the case in terms of the capability of external sorting, then basically you only pay a small number of passes to sort the relations, and your merge process is linear, okay, up to a factor of degree. Okay, since that degree is constant, so that's still constant. So basically, in practice, the cost of sort merge join is almost linear, okay, but with potentially a different constant depending on your join. So that's sort merge join. Okay. Any questions about this? No? All right. So the next thing is the hash join. Okay. So naively, so let's first talk about the simple DB. Okay, when you're implementing the simple DB in this lab, you are going to implement a hash join, right? How do you do that? Actually, so basically, what you can do is you just use in-memory hash table like hash map in Java. Then you build a hash map over the first relation. Then you start using the other relation to probe this. Hash table. Okay, then you can produce the join results. I would say as long as the single DB test framework doesn't complain about the memory usage, then you're fine. Okay. But in reality, of course, in database we need to handle much larger tables than your memory. So building a whole hash table on one of your relations is not feasible. Okay. So what we do here is actually apply a similar approach that we used in hash distinction or hash aggregation, hash grouping. Okay, so basically you first partition your whole table into some smaller partitions. Then you bring in one partition at a time to build a hash table on that. Then what you do is you bring a corresponding partition that has the same key under the same hash function h in the other table, and use that to probe the in-memory hash table you just built. Okay. So because basically the hash join can only work on equijoins. So for two tuples to join, they must have the matching keys. Okay, their keys must equal. So that means they must have the same hash key. Okay, that means basically if you do this partition process first on both tables, you can only end up with joining two corresponding partitions with the same hash key. Okay, you cannot like join two partitions with different hash values. That's the key intuition. Okay. So here, like for example here, for the first pass is here. This is called the partition. Okay, partitioning phase. For the partitioning phase, you basically apply the same thing we did in hash distinct or hash group. You bring in the whole relation and partition that into m over b minus 1 on disk hash partitions. Okay, so each of them will have the corresponding hash value. This is partition. And then once you partition the first table reserve, you partition the second table using the same hash function h into a set of m over b partition of these partitions. Then for each of these partitions, you bring them back into the memory. So basically you use m over b minus 2. Okay, here you use at most m over b minus 2 pages for building the in-memory hash table of the first, like each partition of the first table. For example, here for reserve, you bring in one of the partition into the memory and rehash that using another hash function h2 and build an in-memory hash table on that. Okay, and the maximum memory usage of that is going to be m over b minus 2. Okay, so here it's reserving an output buffer. This is so. I would say if you are doing exercise or in a final exam, if you are doing this, I wouldn't really care about if you minus 1 or 2. Okay, so if you minus 1, that's okay. If you minus 2, that's also okay. If you just simply assume you can use all the m over b main memory buffers, that's also okay. Okay, because that's just some small discrepancy. Okay, that doesn't really matter a lot. Yeah. So once you have that in-memory hash table for one of the partition of reserve, you starting bringing one of the corresponding partition of assailers into the memory, one page at a time into the input buffer. Then you start looping through all the tuples in that partition. Okay. Once you have a tuple, you try to probe the tuples in S that has the same key, okay, using a in-memory hash table. Then if it does have some tuples with the same key, then you have some join results. Okay, and it's done. So that's the hash of. Alright, so let's do some analysis. So suppose your number of partitions k is smaller than m over b. And the largest partition of your partitions is the size of that is smaller than m over b minus 1. Okay, that means basically after the first pass, every partition of your let me say this. So every partition in one of your table is gonna fit in memory. That means basically you can bring every partition of that relation into the memory and build a hash table. Okay. Then you can just do this in two passes. The first pass partition, then the second pass is the join. Okay. So if you solve for the inequalities here. If you just assume your partitions are going to have a uniform size, okay, that's just a basic assumption. In reality, so this might not hold, but people just make these kind of assumptions all the time. Okay. So if you plug in the numbers, and try to maximize the number of partitions k. What you get? You get n over b, that's the number of pages in your file, divided by n over b minus 1, that's the size of your largest partition in that file. Okay, and you get the number of partitions you have after the first phase. Okay, you want that number to be smaller than or equal to n over b minus 2, right? Yeah, don't mind about minus 2. Anyway, that doesn't matter. So basically, that's the equation. Okay, and if you solve for that, that's roughly to say m has to be greater than square root of a. Okay, so that basically means if your memory size is greater than square root of your table size, then you can basically do the hash on in 2 passes. That's the key observation here. So of course there are some constants associated with this. There are -1, +1 at various places, but it doesn't matter. Basically, roughly it goes with this trend. If your memory size is greater than square root of your table size, then you can probably do a hash join in 2 passes. And also, when you are comparing these two, you just need to compare m with the smaller one of your table. Okay. Suppose you are joining reserve and sailors here. You only need to determine whether m is greater than the square root of 500 instead of 1,000. Because in the second pass, you only need to build a hash table for the smaller partition. Right? So that's one. Then, if you can do this in 2 passes, how many hours do you need for doing this hash one? So for the first phase, you read everything once and write everything once. And that's partition, right? So that contributes to 2 times n1 divided by b plus n2 divided by b. Okay? And for the second pass, you only need to read everything once. Right? For everything that's built, that's going to be built in-memory hash table on, you just read them in to build an in-memory hash table. For everything that's in the probing relation, you just read everything, stream everything through that input buffer, and still every page gets to read once. Okay, so that's going to be plus n1 divided by b plus n2 over b. Okay, and that amounts to 3 times n1 over b plus n2 over b. Okay. So in conclusion, basically, as long as your memory size is greater than square root of the smaller relation, the size of your smaller relation, then you can do hash join in 3 times the total number of pages in these 2 relations combined. Okay? And that's a linear class. Of course, in reality, of course, we made some assumptions like uniform sized partitions, right? But if you do have a very skewed data set, like so almost all the keys have the same value, and with this approach, you are basically cannot do that. One of your partitions is going to be so large. But in reality, in a benign case, in a general case, it's fine. And also, there's a small comparison here, right? Here we say your m needs to be greater than square root of a smaller relation, right? But before, when we do this refinement or sort merge join, we also look at how many, what's the memory size requirement so that we can do the refined sort merge join in 2 passes, okay? So our result would be m over b greater than square root of L. Is that L the same thing as the n in the other equation? Inequality? No, right? Here you must, you have to guarantee that the larger relation will fit in memory in the second pass, right? Because you are basically doing the last pass of your external sorting and the merge phase of sort merge join at the same time. That means you need to keep one page for each run of your larger relation in memory at the same time. Okay, so you cannot just fit the smaller table in memory once. Yeah.
So if the data is not like neat how it used to be,
Right.
can you just make like a worst case scenario?
Right. So yes, I actually. So in the next lecture, we will actually going to talk about that. But yeah, it's a little bit complicated. Actually, in database, they keep some kind of statistics like histograms, so that they could possibly estimate what's the largest size. Okay, that's one thing. And the other thing, usually these algorithms are written in a graceful way, so that if they do fit in memory, then it's in memory. But if it does not, then it will spill to the disk. Okay, so it's in the same spirit as the hybrid hashing, right? So basically, if your table is small enough, it can fit in the in-memory portion of your hash table, or whatever thing you need, right? You can basically just use the memory portion, okay? But in the case your table is so large that which you do not need to determine beforehand, okay? You basically create a bunch of spill partitions. Those are the partitions we used in hybrid hashing, right? You start dumping additional like spill tuples into those partitions, and then you come back to process that when you are done with the email. That's the typical approach. All right, so yeah, so that's hash on. Any questions? Yeah.
So this is also assuming that the amount of memory required for the in-memory hash table is linear to the number of tuples that we have to store there.
Right.
But
It doesn't take into consideration the what's that, load factor.
Okay.
Yeah, typically you still need a load factor to take into consideration, but this is just very simplified.
What's a realistic load factor given our lectures on?
Yeah, so I'm not really sure about what's a choice, but I would say 1.2, 1.25 up to maybe 1.7 is reasonable. Okay, that's a reasonable estimate. And also, like if you do like if your memory is so tight that even exceeding 2 times your things doesn't fit in memory, then it's probably an indication that your system needs an upgrade. Because in reality, when you are using a database, you specify the maximum size of memory to the database, but that's not usually the size of your memory in your system. You still need to reserve things for other things like system I/O buffer, like system kernel space, right? Something like that. So you typically won't deplete all the memory you have on your system. So that should be typically should be fine. Yeah. Any more questions? Okay. So then for general join conditions, suppose you have equalities over several attributes and connected with n. That's basically conjunctive predicates. Then you could build a multi-column index, like index over multiple columns. Then you can do the selection, right? Or alternatively, you could also use existing index on one of the columns. Like here, for example, for the first one, you could either use SID and SName as the column, the key column in your index, or if you have an index on SID, then basically you can just apply the first portion of your join predicate, then apply an additional filter on top of that. Okay, that's another or if you are doing sort merge or hash on, then basically you are sorting things or joining things, hashing things on the fly. Then you can just use those columns as your key columns, your sort or hash algorithm. Therefore, in equality conditions, really you cannot use hash on, right? I wouldn't say it's not necessary you can't use sort merge join, but it's not typically it's not a good choice, right? especially if you have an open-ended range of, like this. If you say R dot R name is smaller than S dot S name, then whenever you have a tuple of in R, then the range of your S is basically everything after this, right? In your, if you have an index in your index, right? Or if you have a sorted run, that's basically you search for this particular key in S, then everything after that is going to join with this particular tuple. And solid merge join is really not a good choice when you have a large join result. Right? For index-based loop, you could use the B plus tree. Of course, it's the same problem, but basically you still need to join everything after one, like after one key, right? It's basically probably the same problem. Okay, but for index, typically you could have a smaller. One thing is that you could have a smaller data entry. That's one possibility, right? If you do use alternative to data entry, then and you have all the columns in that data entry, then you could potentially scanning fewer pages than you do a sort, right? Or if you have a cluster index, I would say it's basically you can just probe where that first key is and start scanning everything. But still, it also still depends on the selectivity of your join. And also, in a really expensive join, like it's almost Cartesian product, really the best choice is basically block nested. It's not necessary in the sense of complexity, right? So even if you have a certain selectivity, and you can derive a lower complexity for index nested loop or solver join than block nested loop, but in reality, because the block nested loop is so simple, it could have a much lower overhead on the system, so that on a typical data set, it's going to run fast. Okay. But it really depends on what's the specific scenario. Okay. Yeah. So for a general, really, so for an even more general join predicate, really your only choice is just nested, unless you come up with something fancy. Okay. So the last bit of this is set operations. We haven't touched set operations since the relational algebra. But anyway, so if you're doing an intersection, it's basically a special case of join. You're basically joining every attributes, right? You use the entire schema as your join attributes. Or if you're doing cross product, that's also a special case of join. Basically, everything qualifies as a join. If you are doing union, if the union is not distinct, then that's pretty easy. You just append the result of another table to one table, right? That's easy. But if you do need to do a distinct, then it's a little bit more complicated. So we could use a sort-based approach where you basically sort two relations and start doing a merge. Except in this merge, you only merge like if you encounter two duplicate keys, you only keep one of them. Okay, that's the merge. Alternatively, you could also refine the whole process so that you can combine the past zero and the merge. Okay, so potentially you could, whenever you are sorting a run, you start merge that run with another run from another table on the fly. Okay, and you can drop those duplicate items like early in your stage. Like you can produce a smaller intermediate output. Okay, that's still design choice, but I don't think that's going to contribute too much for that. For hash-based, basically you just use the hash run you mentioned. Basically, you you partition everything into smaller partitions, then build a hash table on top of one of the partitions in one of the table. Then you choose the corresponding partition in the other table and start streaming that partition and loop through all the tuples in that partition. Okay, and once you find you have a new tuple, you probe the in-memory hash table for to check for duplicates. If it's a duplicate, then you drop it. Right? That's the approach for distinct unit. Then except is basically the reverse of the opposite. Sorry, the reverse of the logic. Right. Okay, and also there are some impact of buffering, right? So since everything in a database are actually accessed through the buffer pool, it actually your buffer management is going to impact the effectiveness of your memory usage. Like if you happen to have a large relation, so that you are starting scanning through this relation, okay, and then your buffer pool uses an LRU. Okay, we mentioned this before. Well, what's the problem? It's a problem. It's a problem called sequential flooding, right? If you do use a sequential, like if you have a large file like this, and you only have a small amount of buffer pages, once you start reading the pages here one by one, you are gonna replace the old furthest accessed page in the buffer, right? So let's say this 1, 2, 3, 4, 5. You start putting 1 here, 2 here, 3 here. Also, you need to read 4. If you are using LRU, you are going to replace the oldest accessed page in your buffer pool. So that's going to be 1, right? You replace that 1 with 4. Okay. So as you scan everything here, you read everything once. Okay. And if you are scanning this whole file once and once and once again, effectively you are not using the buffer pool, right? Nothing is buffered. So the best strategy for that is actually you just ping a small number of pages at the beginning, right? Because your file doesn't fit in buffer pool anyway. Or this is if you only have one query like this, then this is the case, right? But on the other side is that if you have a couple of concurrent queries or transactions that happens on the fly, so you are basically polluting the buffer pool with a small set of your pages in your query, right? That's actually not a good thing because so typically if you have other queries which require a fewer number of pages, it's typically a transaction, like you are updating something or inserting something. It requires extremely good latency. Like it needs to have a short latency. Then you might want to prioritize your buffering towards those transactions instead of this long-running scan, right? So in order to not to pollute the buffer pool, sometimes people use a ring buffer just for scanning a whole file. Okay, you can just allocate like 32 pages for a ring buffer. Then when you're scanning this key file, you just put things into this local ring buffer instead of the general buffer. Okay, so that other ongoing transactions like insertion and deletion or updates, they don't get affected. Okay, by this scan. Those are basically all the considerations. And also, so when does this happen? Like the sequential flooding problem. Okay, so for block nested loop, it does affect the buffer replacement policy. It does affect it a lot, right? Because in block nested loop, you need to scan one of the file again and again and again, right? So that's exactly the same problem we have mentioned here. So what about index nested loop? In index nested loop, you only scan one file, the file of outer relation once. right? But for the inner relation, you do not scan that. You use the index to probe for the thing, right? So that actually doesn't really matters a lot, unless your file is classed, okay? Unless the inner relation is classed. For sort merge join, it doesn't really matter because sort merge join, everything is only read once and read once. Even for the intermediate result or the base table, everything is just read once, exactly once. You do not come back to the same page. Okay. So sort merge join is typically not affected by the buffer replacement process. That's the impact of buffer. So in summary, we have talked about a bunch of operators in relational algebra and how we actually implement these operators in database. And also we talked about many alternatives for especially those complex operators like joins, distinct, group by. Okay. And when you are considering all these alternatives, it's really not an easy problem to solve. You need to take into consideration a lot of factors like buffering, memory pool size, file size, data distribution, a whole bunch of different things. And you typically do need to make a lot of assumptions. That's where our database, the inefficiency of our database comes from. So that's it about query evaluation. So next, I'm going to talk about the query optimization. Okay, this is a very related problem. So, as we said, when we are doing executing a query, we have a data flow model where we have a Volcano model. You just have a data flow of operators, right? Whenever you are executing the queries, this is you basically pull the tuple from the topmost, like the operator on the top, and that in turn starts pulling records from its child operators, and so on, right? So really, this actually has a lot of different implementations as we have shown in the previous lecture, and also you have different orders of applying these operators. Okay, you can generally reorder things. So this is a really complex problem. So in the first part of this lecture, I'm going to using the same example we are using here, like here. So we're doing a simple two-table join. You join the reserves table and the status table of the same schema here, the same stats. And they are joined on the SID attribute here, and you apply two additional filters. Okay, you have a filter that finds all the boat ID with 100, and you try to find all the sailors with ratings greater than 5. Okay, that's the join query. So in a nutshell, basically in a query optimizer, we call this whole thing as a plan. Okay, a plan is roughly like it is just the tree here. Okay, a plan is basically a logical plan is basically all the combination like combining all the relational operators and organize that into a tree. Okay. And if we also call a plan of like you could also if it's instantiated into physical operators, then it's a physical plan. Okay. So for a logical plan, basically you need to choose what specific implementation or algorithm to use for each of the operators. And also you need to decide in which order you want to apply these operators. Okay. So ideally, we actually want to find the best plan, but that's not always possible, okay, because we do not have enough information here. So in reality, the best thing you can do is just avoid the worst plan. Okay, don't do stupid things like computing the Cartesian product of everything if you do not need to. Okay, that's basically our goal. So let's recall the iterated interface. I think that should be fresh to like each of the operator here. It has a bunch of different interfaces that it's required to have. Like you have open, which initializes the state, and get next produces the next tuple, like the next result from this operator, and close basically cleans up everything. So in general, the whole workflow of executing a query is basically from a query, which is in the SQL syntax. It's a text, a short segment of text. It's passed to a query parser, a SQL parser. It passes that into a parse tree, which we sometimes call it a logical plan, or just parse tree. Then the query optimizer starts generating a logical plan out of that parse tree. Sometimes it's the same, or it could be in different orders. Like typically, the ordering happens during the logical planning phase. Okay, and then based on that logical plan, we might need to actually choose which physical operator we want to use for each of the operators in your logical plans. Okay, then you generate a physical plan for execution. Basically, here the physical plan is passed to the query executor for execution. Okay, so when you are doing this plan generation, you sometimes you need to invoke another component called plan cost estimator. Okay, that's basically to estimate what's the cost defined in a certain way of executing a particular plan. Okay, and then that cost estimator also needs to consult maybe the schema, because sometimes when you're doing projections, you might need to compute what's the reduction ratio. Okay? And or you could also refer to the statistics, which are actually collected during runtime. Okay? So initially in your database, you don't have any statistics. So basically everything is just a guess. But as time goes by, you execute the query over the same table again and again and again. This query executor actually collects a lot of statistics about the tables. Okay, it might have a histogram on the some of the columns that frequently appear in one of the joins, or it could also have the number of tuples in one of the table, or how many distinct values you have in that table. So that those all serves for the purpose of cost estimation. Okay. Right. And also note here we didn't explicitly list the logic plan, physical plan here. Why is that? Because in reality, so although people tend to first do the logic planning and then do the physical planning, but in certain systems it might be combined together or they can be mixed together. Like sometimes you do reordering in logical planning, but in some systems you may want to do that in physical planning as well, or you put some physical planning into that. So that's actually a mixed state, I would say. Okay. So really, you cannot determine which one is best. But that's why it's typically mingled in this whole process. Right.
In a lot of the more optimized physical operators from the previous slide deck, it seems like you just combine everything into one.
Right.
Like the more the more efficient it gets. So realistically, when you generate physical plans, do we tend to just end up with only a couple operators that are all very tightly?
Right. So do you just consider a specific type of operators, or do you consider the whole plan?
I guess I'm just wondering, like, do we end up with just like one operator that we have a bunch of flags that we use to tune, but then it kind of just merges all the different operators together?
Oh, yeah. So actually, it's a little bit complicated to answer this question. So it's hard to say. You can, if you want to simplify things, then basically, ideally, you just have a bunch of options for each of the logical operators, right? But in reality, of course, some operators must come after specific operators, like distinct must come after sort or hash combine, right? Something like that. So then, the problem is that they have kind of dependency among them, right? So in reality, I would say they have some way to enumerate all the choices on the fly. Okay, but really it's just it's half heuristic, half dynamic program. or even more complex, sometimes they use, so in PostgreSQL they use what's that, simulated annealing, those kind of things. Or it's not simulated annealing, it's a inheritance algorithm, something like that, genetic algorithm, something like that. So it's basically based on both heuristic and local search. Okay. Sometimes when the number of tables is small or the number of choices are smaller, they could use some sort of dynamic programming, which are not optimal, of course. They just tend to be optimal in a confined space. And we will talk about that later. It's very true. So here, for the example, we still use the very same schema, and we have a bunch of new statistics about them. So let's say we have 100 votes. Okay, we have 100 votes. That means we have 100 different BIDs. Okay, and also that means, so if we assume uniformity among the votes, then you have roughly a thousand tuples per vote. Okay, so for each vote will have roughly 10 pages. Okay, in reserve. And the other one is for sailors. Let's suppose you have 10 ratings, okay? 10 distinct ratings. And also, if you assume uniformity, then basically you have 50 pages per rating. Okay? Those are basically all assuming uniformity. Then let's assume we have 5 pages in the bottom. Okay. That's M over B is 5. Alright. Let's go with the simplest plan we might come up with. Okay, it's a naive plan. It's just in the same order as we've shown before, and it uses basically the simplest join operator you could use, page-oriented nested loop. Okay, so that was the cost. The cost would be, so for the sailors table, you don't have suppose you don't have index, then you need to scan everything, right? You from a heap. So that's a heap scan. Here is a heap scan. And then for reserves, it's also a heap scan. Then on top of the result of heap scans, you apply a page-oriented nested loop. Then you do the filter on the fly and do projection on the fly. Okay. So let's assume our goal of optimization is to find the most efficient plan that computes the same answer. Okay. So how do we define the efficiency here? Let's suppose we just compute how many IOs we need. Okay. We just care about the number of IOs. We don't even care about what kind of IO we're using. We're just counting how many IOs we use. Okay. Then for this simplest plan, the IO cost would be 500 plus 500 times 1,000. Okay, that amounts to 505,000 IOs. Right. Right. That's oh sorry, 500,000 and 500 IOs. Okay. That's the number. So why is that? That is because suppose the relation on the left is the outer relation. That's the relation you iterate through. And the other one is you repeat the scanning once and once again. Okay? So for each of the page on the left, you scan that once. And then for each of that page on the left, you scan the whole file on the right. Okay? So how many pages we have on the left for sailors? That's 500. So this is 500. And how many IOs are paid here? You pay that for 500 times, and each time you scan the whole file once. So that's 500 times 1,000. Okay, so that gives us the number of IOs. Of course, the upper two operators doesn't incur any IO because they are basically perform So they are purely in memory. Okay, that's the number of IOs. Can we do that better? So one observation is that we could potentially push down one of the selection predicates down to the heap scan. Okay, we can push this one to here, and we end up with something on the right. Okay, so basically, when you are scanning the tuples from the Sailor, you apply the filter on the fly. If it passes the filter, then you do you start like if it passes the filter, you put that into one page. Okay. If it doesn't pass the filter, you just like drop it. Then what happens is that you scan everything here once. You have 500 pages, so that's 500 IOs. But what's the number of tuples you have in the end? So assuming uniformity, we know there are roughly 50 pages per reading, and there are, let's say your reading is from 1 to 10, then you have 5 different readings that is greater than 5. Then you have 250 pages instead of 500 for like as a result of this filter, right? And for each of those pages, you scan a result once and do the page-oriented method. Okay, so then your cost is brought down to 500 plus 250 times 1,000. Okay, and that gives you 250,000 and 500 items. Okay, that's the answer. Okay, that's when you push down one of the operator. The selection predicate. So what if we push down the other one? Does that help? No, that doesn't help actually. Why is that? The reason is that when you are scanning, so for each of the page as a result of here, you need to rescan this result from scratch, right? Because you do not materialize the result of this selection predicate. So they are not saved, and you need to rescan everything whenever you have a new page on the left. Okay. Yeah.
So instead of sailors on the web, can you do a reserve, because each reserve has just 10 pages.
Right. That's a good observation. I'm just going to show you the next slide. No, it's totally fine. That's a very good observation. Okay. So like here, the key point is that, so if you push down non-materializing selection predicates down to the inner relation, it doesn't help. Okay. So that's the key point here. Like following your idea, it's basically if you swap the two relations, like you use reserve as the outer, sailors as the inner, okay? And you also push down the selection predicate for reserve. What's the number of IOs? Okay, let's do some calculation. So you have 1,000 pages to scan in reserve, but how many pages do you have in the end? It's only going to be 10 pages, right? For each of this page, you scan the whole file of sailors ones. Okay, so it's going to be 10 times 500. Okay, and the end result would be just 6,000 IOs, right? That's the end result. You only have 6,000 IOs instead of like 250,000 IOs. Okay, that's roughly a reduction of 2 orders of magnitude. That's good. And then, so we've already said that if you push down the selection predicate to the inner relation, that doesn't help. But that is due to the reason that you have to rescan the sailors every time you scan it, right? You pull a result from the selection predicate. But what if you materialize the selection results? Okay. What if here you materialize all the results after the filter to the disk? What's the total cost, right? So let's still do some calculation. So for here, you still scan all the tuples in reserve spawn, so that's going to be 1,000 IOs. Then you scan the sailors, each of the page in sailors once. That's 500 IOs. But as an end result, you only produce 250 pages to write to the disk. So that's going to be plus 250. That's output, right? That's output. And that's the output of this selection predicate. Then you start doing this page-oriented nested loop. For each of the 10 pages on the left, you only need to scan 250 pages on the right instead of 500 because you have materialized the filter result to the disk. Then if you compute that, the number of IOs is further brought down to 4,250 IOs. Okay? It's roughly 2/3 of the original plan. Okay? Sorry, the previous plan. So it's better, but can we do even better? We swap the two relations again. Okay, let's still use sailors as the outer, but reserves as the inner. But you do the same thing. Basically, you push down the selection predicate for the inner and materialize that filter result. Then the result comes down to 4,010 IOs, slightly smaller. Okay, so that is tricky. So if you do not do materialization, then it's better to use reserve as the outer. But if you do use materialization on the inner relation, then suddenly it becomes to be sailors is a better choice as the outer relation. Okay. So then you see why this is tricky. Okay. So is there anything else? Can we do sort merge on? Right? We can use a more sophisticated join out. Does that help? If you do the calculation here, here I also updated the slides. I think on the slides in Canvas, this is 3, but if you calculate that carefully, actually you need 4 passes to sort the sailors relation after the filter. Okay, so let's review what's the process. Okay, so first you scan the reserves table and apply the filter on top of that. After that, you only get 10 resulting pages. Okay, so that's scanning 1,000 pages for reserve and write 10 pages back to disk. Okay, and then you scan the sailors, all the 500 pages in sailors, and write the 250 pages back to disk. Okay, that's a result. Then you have 10 pages here and 250 pages here. Then on top of that, you do sorting on these 2 temporal relations. Okay, so if you have just 5 buffer pool, then you need 2 passes to sort 10 pages, and you need 4 passes to sort 250 pages. Okay, so that gives you the number of IOs for the 2 sortings: 2 times 2 times 10 and 2 times 4 times 250. Then finally, you do a merge. Okay, so since we are still merging on the primary key and foreign key, so the merge cost is still linear to the number of pages you have in these 2 temporal relations. Okay, so that amounts to 10 plus 250. Okay, if you add everything up, it's going to come to 4,060 IOs. It's slightly worse than you do a naive page-oriented nested loop, right? You see the reason. So this is actually because, right, the reason I think is because you have a relatively large selectivity. Okay? The number of join results is relatively large compared to the full relation. So that's why the other way is better. So the next thing, if you do use a block nested loop, what is a block nested loop? Okay. When you're doing the nested loop, you have a 1 page for the outer relation, then you start scanning through the other page in the other relation, but you only utilize 2 buffers at a time, right? But you can actually reading like 4 pages for the router relation at a time. Sorry, 3 pages. You need to leave like at least 2 buffers for the other one. So if you're reading 3 pages on the, of the outer relation at a time, but like that iterate through the inner relation for each of these 3 pages, how many passes do you have? You have 10 pages in total, and you're reading 3 pages at a time. You only do it for 4 times, right? So then you only iterate through the inner relation for 4 times. Okay. So if you still use the query plan we used before on the right, okay, use the query plan on the right, then your cost is going to be 1,000 plus 10 plus 500 plus 250. Then for the join cost, it's only 10 plus 4 times 250, right? And that comes down to 2,770 IOs. It's really roughly like 3/5 of the IOs you would use okay, or just a page-oriented nested. So that's even better. So then you could also push down the projection. Why does that help? Right? Because we are actually materializing the pages. Right? We are materializing the pages. So since we're materializing the pages, if you have fewer like columns to write, then you have smaller size of relation. Okay, so that means your intermediate size of relations is going to be smaller than 10 to 150, right? So then, if you do some calculation, it's going to be the total number of IOs is going to be smaller than 2,000. Okay, it's even better. Of course, when you are doing when you push down projections, be careful that you cannot just push down the columns that appear in the final result. You also need to push down every column that gets referenced in your intermediate operators. Like here, for reserves, you can just push down SID. For sailors, you have to push down SID and SNAME, right? Because although you only need SNAME at the very top, but here in the join, you do need SID, so that's why you cannot leave out the SID. Okay. So when you are pushing down the projection, be careful about that. All right, so I think it's almost time. Let's talk about other stuff next time. So we will see more plans, alternative plans. Okay. Okay. See you next time.
So with the projection, after this,
So because
yes. I think like a steam machine, yeah, the certain state and come back in. Yeah, that same state.